Okay, in this video I want to discuss with you the kinetic theory of gases and how we can derive gas laws from the kinetic theory of gases. Now, the first postulate of kinetic theory of gases, recall, states that gas molecules move in random motion. And when I use the word random motion, that basically means that the speed with which the molecules are moving, so the speed as well as the direction, both of those are variable for each molecule. Are variable. And that would mean that any property such as the kinetic energy, such as maybe pressure, all of those are going to be studied as a net average for the entire system. That means one cannot say that, let's say you have these 5 gas molecules in a balloon, you cannot really say that the pressure of one of the balloons right by the side is perhaps 1 atmosphere and the one at the center is perhaps 2 atmosphere. It is going to be measured as a net average for the entire system. Now, let's say we have a balloon. I'm showing 5 molecules for that right now. What would happen if you try to decrease the volume of the system? So what would happen if the volume decreases? Realize that as the volume of the system decreases, that would mean that now you have the same 5 molecules, but now they are restricted and confined in a smaller space. Don't you think that that basically means that the particle density has increased? The particle density has increased, and hence the probability that a collision would occur, that will be higher in this case. Collision will occur. So one can say that the pressure of the system is going to increase. So as volume decreases, pressure increases. Well, that is what Boyle's law is. So I have given you one. You can try Charles' law or Dalton's law of partial pressure, whichever you want to go with. But realize that pressure, which is proportional to the concentration of the molecules, and it is also proportional to the velocity of the molecules that are moving with, because both of those are going to increase the probability with which the molecules are going to move around, collide with each other or with the walls of the container. And as you reduce the volume, the probability that those events will occur is going to go high, and hence that will ultimately culminate in the increase in pressure, showing the inverse relationship between pressure and volume, which is nothing but Boyle's law. Okay, let's take a look at the ideal gas law from kinetic theory. So as we know that pressure is proportional to the frequency of collisions and also the average force with which those collisions are occurring. And you can hopefully see from physics that the average force is going to be proportional to the mass of the particles. It is also going to be directly proportional to the velocity, because you know that force is equal to mass times acceleration. So the change in velocity and the mass, those are the two deciding factors that essentially give you the force associated with a particular collision and hence the pressure associated with that. So one might be able to say that force is proportional to m times v, but again from physics, m times v has a name associated with that, that's called as the momentum. So one can say that if the momentum of a collision is pretty significant, the force associated with that particular pressure, with that particular collision is also going to be significant. Let's see how frequency of collisions, what are the factors that frequency is based on. Frequency is dependent on velocity. We can say that for sure, because higher is the velocity, then the probability or the number of collisions occurring in that sample is going to be a lot higher. Of course, we have seen in the previous slide that if my volume is small, then the frequency of collisions is going to increase, and vice versa. If I have a larger container, then the probability that a lot of collisions are occurring is going to be pretty low. And of course, it also depends on the particle density, the number of molecules, Larger is the number of molecules. That means if the concentration is high, that would mean that the collisions that are occurring is going to be significantly large. So if I put all of these factors together, I can say that my frequency factor is going to be proportional to the velocity times 1 over volume. I'm keeping a small v for the velocity, 1 over capital V for the volume, times the number of particles, and we can say that the force factor, so this was frequency, the force factor, that is simply basically proportional to mass times the velocity. So if I combine these two, I can say that pressure is going to be proportional to velocity times 1 over volume times number of particles. All of that is being multiplied by m times v for velocity, and that would mean that pressure is going to be proportional to 1 over v times n mv square, or one can say that pressure times volume is proportional to the number of molecules associated with the system, and mv square. Now you know that kinetic energy is half mv square, right? Half mv square. And you know that kinetic energy is proportional to temperature. It's in direct relation to the temperature. So one might be able to say that pressure times volume is going to be proportional. It's going to be proportional to the number of particles that you have in the system times T. And now, since number of particles can be associated with the number of moles, one can say that pressure times volume is proportional to the number of moles in the system times the temperature. When you remove the sign of proportionality, you have to introduce a constant of proportionality. So PV is equal to nRT, where R is the universal gas constant that we talked about in class, having a value of 0.08206 liter atmosphere per mole per Kelvin.